Hello, y'all. Barry Bever Jr. back for some more physics. So, some more physics. Oh, hold on. Audio and everything seems to be working fine. And I'll be doing a problem that was presented by the organic chemistry tutor, a similar problem to what we're working on in my foundations class to review undergraduate physics stuff. I think I'll do it slightly differently than the way he did it, but we'll see if I get the same answer. So basically, we have a static problem. So what this simply means is that nothing is moving. So if we look at this problem, there's a hinge that torque can move around. Then there's masses with weights pulling down. There's tension in this rope or string here. So one interesting thing is that the torque is going to be 0 because nothing is moving. And the force equals 0. And this will basically be torque clockwise plus torque counterclockwise. And this would be force in X plus force in Y. So all we have to do is identify all the forces by doing the basic Newtonian force diagram. Then we'll calculate some things and see if I get the same answer that the organic chemistry tutor got. So looking at this, we have the downward force here, which is Fm. We have the downward force here, which is Fb. Fb for beam, Fm for mass. We have this force that is pushing outward because it's not going through the wall. And we can see that the tension is pulling this way. And that's simply T. So being that it's not pushing through the wall has to be pushing outward. So we have FH X, and we'll call the force down the center of the beam FH. So then we have FHY. So those are the forces. And one difference between the way I did it and he did it, I think that's all that we need to solve this, but just in case, I'll put that we have the tension for the mass going that way. We have the tension, or the torque, I meant to say the torque from tension going that way. So the torque from the mass going that way, the torque from tension going that way, and the torque from the beam going that way. If I consider the hinge the focus of torque. One of the things I learned from the organic chemistry tutor is how, which reminded me that Professor mentioned that as well, that you can pick whichever position is convenient to calculate torque from. So I can calculate torque from here in the middle, or I can calculate torque from right there. If you can calculate torque from different places, it's convenient to calculate torque from one of the ends, because then there's no torque coming from the hinge, so therefore you have an equation that cancels out one of the variables, which makes it easier to solve. But let's see if we can do it without that. So to add up everything on the x, we have e to the left must equal FHX to the right. Again, because it's static, everything has to be equal. And for the force down, we have Fm plus Fb. And that's going to equal FHY. So to highlight these to make it clearer, these three forces going up and down. It's this one, and this one. And these two forces going left and right is this one and this one. And that should take into account all the forces at play in this scenario. So what I'll do now is start to calculate everything. I have my keyboard out the way, but I'm watching the live chat, so if anybody pops into chat, I'll put this on a little stand so my keyboard is not accessible at the moment, but when I see you all, I'll move it in. Boom. So to find out what all these forces are, we know that Fm equals mg, which equals 15 kilograms times 9.8 meters per second squared. So that equals 147 kilograms. And FB equals mg, which equals 20 kilograms times 9.8 meters per second squared, which equals 196 kilograms. Interesting how these give even numbers, but it is times 10 and is only to the 10th decimal place, so that makes sense. Like, this is a 10th number, and this is only, it has a 10th decimal, so it makes the decimal go away. You know what? Because the last number ends up being a 0. So 5 times 0.8 is 40, so the last number is 0. And 0 times 8 is 0, so the last number is 0. So there's a 10th decimal, but it's 0, so we don't have to worry about it. So that means that FHY equals 343 newtons. Oh, and this is not kilograms, this is newtons. We have that. FHY and now an interesting way to get FH and then FX and then T, you can actually get that from here, is because this angle is going to be 30 degrees as well, because the tension is horizontal, it has 30 degrees to the beam. So the horizontal anywhere along that line will have 30 degrees to the beam. So this is 30 degrees. So we know that FHY equals FH sine 30 degrees. So that means that FH is FHY divided by sine 30 degrees. So that's going to be 686 newtons. So sine 30 is 1/2. So that means that FHX equals FH cosine 30 degrees. So I had FHY, use that to get FH. I was wondering if there was a way to go straight to FX from the FHX from FHY. I don't think so. Or maybe. I mean, technically, I could have just solved FH for cosine, but it ends up being the same thing. I would just plug in FH. So basically, yeah, it's FH times tan 30. Oh, it doesn't matter. So this is going to be 686 newtons times cosine 30, which is going to be thinking about the unit circle. That's right, square root of 2 over 2 is the one we're the same. Then it goes about the unit circle a bit. So that times 686. This is 594 newtons. So what that means is that the square root of v squared should equals FH. It does. All right. And since T is FHX, that equals T. Let's see what they got. They got a slightly different number. So they did get this for that. FHY, they got 594. Which means they got FHX, they got 530. So when I plug their numbers in, let's see here. I wonder if oh, it should. Since the FHX and the FHY are components of FH, the sine thing should work, and the squared thing work. In other words, FH equals square root of FHX squared plus FHY squared, and it does equal 686 newtons when I plugged it in. So why don't we try it the other way, and we'll see if something different happens. But this is what I have for T, for FHY, for FHX. This matches what they have. So why don't we look at the torque? So it's static, is not moving. So the torque of tension equals the torque of the beam plus the torque of the mass. And torque equals F cross R, which equals FR sine theta. And R equals distance to the pivot point. So what we have is the torque of tension So tension R is going to be not all the way to the end. We're going to have 4 meters. We're going to have 30 degrees. So sine theta equals opposite over hypotenuse, which equals 4 meters over, we'll call this little l, the distance to the tension wire. So just this part here is little l. So L equals 4 meters divided by sine 30, which equals 8 meters. Right? This is a right angle. This is perfectly horizontal. So what that means is that torque for tension is going to be, well, maybe I'll solve for that. I don't want to use my each x that I solve for, because this is the one I'm uncertain about. So why don't we just solve for it with the other tensions? So T torque is going to equal the torque of the beam. So it's going to go from the center axis So this is going to be FB. The radius is going to be from the center of the beam, so that's 5 meters. And sine of theta. So the angle that the torque is pulling from is 30 degrees. So we can say that, because if it was 0, there would be no torque. If it was 90, it'd be 100% torque. So it's 30 degrees, so that's the angle that you use, the angle right there. So this is going to be 20 kilograms, 9.8 meters per second squared, 5 meters, 0.5, times 9.8 times 5 times 5 equals 490 newtons. I believe he calculated this, calculated it the same way. So where were we? It should be beam, tension, the torque of the little mass will be F little mass, and that's at 10 meters. Sine and the angle here will necessarily be 60 degrees because it's the other half of the right angle from 30 degrees. So that's going to equal 15 kilograms, 9.8 meters per second squared, 10 meters, and question that torque has the units of energy, right? Because you have force times uh, force times distance. Oh, yeah, because energy is kilograms meter squared over second squared. Torque is kilograms meter squared over second squared. That's interesting. And this is going to be sine 60. So this is going to be 1,273 joules. And let me check. Yep, seems good. And then we have the last one, uh, tension. No, that's it. So that means that tension T equals 1,763 joules. Right. So what can we do with this? Tension T is 1,763 joules, which equals uh, T R T sine theta, which equals T R T sine theta. This is by the definition of torque. And the angle is going to be 30 degrees. Already calculated the distance of 8 meters. So this is how we can get the distance that we need. To me, the force that we need. So 1,763 joules divided by RT sine theta equals T, which equals 1,763 joules divided by, what was that, 8 meters sine of 30. So that equals 1/2. So that's 763 joules divided by 4, which equals 440. And this is Newton's motion divided by the meters. I believe that uh, mass. Oh, that's what I did wrong. It's because I still use 30 degrees here. And it should be 60. So I guess because I was looking at the 30 there, that's 60. So this is 60 degrees as well. So the torque for the beam is going to be the force beam 5 meters, 60 degrees. That's where I made my error. They're going to be 20 kilograms sine 60. Let's see what this is now. This is actually 840, 848.7 joules. And now you can add this up to get the full tension. So this plus 1273 equals, so this is 2,122 joules. Okay, so now my numbers are matching up to what he had. So 2,122 got about 4 equals 530.5. Okay, 531 newtons. And this means that the angle thing currently, I mean, it should still work for the Fy. Fyh is that sum. I think it's Fh sine 30. So this seems to not work to get the full Fh. It's the only thing I could imagine at this point. You can get the Fh of y and Fh of x, but you can't use it to get the reverse from sine. In other words, you can get Fy from summing their additions, but you can't use trig. So I have to ask about that, why that doesn't work. We know this is the case because this is a direct addition from what it equals. We know Fhy has to equal all the other things pushing down. I guess because the weight that's pushing down doesn't necessarily have any bearing on what's pushing in or out or not. So it must just be a matter of the fact that, in other words, if I kept the tension the same, the tension and the wire the same, but I put the bigger weight here, is not going to change the x-axis force. It'll change the torque. But as far as the force that's pushing down from gravity, which is pulling straight down, is not going to change the x value. So I have to remember that fx is not necessarily, fs and xy is not necessarily based upon the sine cosine thing in these problems, which seems odd because if you put more weight there, it seems like it should pull on the tension wire some more, but at the same time it's pulling on it straight down and the tension wire is pulling straight to the left. So perhaps it's just that this problem is not a physical problem in the sense that it's not, perhaps in the real world, the materials would not be absolutely static. So there would be a little bit of sagging and deformation, and thus there would be some Y component to this tension wire in the real world where matter bends and deforms according to forces. So perhaps that could be what it is. This is a very ideal situation. In the ideal situation, the horizontal weight or force is independent of the vertical because there's other things that's causing it to be horizontal, namely the masses that you add, which you can add independently of the Y value. So that's what I'm seeing is going on. So the only way to get the horizontal is to use the torque, because the torque is working in a horizontal direction. So that's something to keep in mind. That's something to know. It's awesome. On about an hour. I started a bit earlier than my normal time. I'll go ahead and end here. I saw a few people pop in. Hopefully you all enjoy. Like, subscribe if you haven't. Let me know if you have any questions, and I'll see you all next time.